people would say, can you do anything in C++ if you can't do that? So OpenACC 2 has the idea of an unstructured data region, where you basically say, this is where my data region starts, and this is where my data region ends, but these can be in these separate routines. These could be in these constructor-destructor methods. It could be inside Fortran derived type methods. You could just use it in your ordinary code if you want, but an ordinary data region is probably enough. And so the idea there is that basically, if data needs to move to the GPU, you say that at the enter thing. If data needs to come back from the GPU, you say it at the exit statement. That should say exit there, by the way. Sorry. I'm not going to go into what all the clauses are and all the things, but when you're doing that sort of unstructured data lifetime, there is a way to do it. Is there a way to say, this thing is declared in some module, in some shared file, in some header file, just always put it on the GPU straight away? Is there a way to say it's always on the GPU? The declare directive is a way of doing that. And there are some clauses to do with whether you should actually put it on the device or whether you should just say that it is capable of always living on the device, and you will move it at some later point in the code. So, if you've got a big data region that's your whole code, maybe instead you just want to use declare to do it. But this is an OpenACC 2 feature. So if you use an OpenACC 1 compiler, it's not going to support that. So these are some examples of doing that. And this is an example of an unstructured data lifetime. Here, I have an enter one where I put A and B on. I can have separate places where I take A off the device. Here, I don't do any data movement. I just delete it. I just do a mem-free on it. Here, I copy the data back. And these are separate, even though these were together. What you can't do is move the same thing off twice. I don't know. I think it's the case on a Cray system that it cleans the node up after you anyway. Yeah, that's possible. I think that will be compiler dependent. I think the Cray compiler cleans up, and certainly the Cray job control system cleans up the node. Good question, but I don't know. So another way is that what happens if you want to call a function within a parallel region? How do you do that? At the moment, you can do it by inlining. The compiler actually inlines the function. That's not ideal for a number of reasons. One reason is that it may be a lot of code to inline. Another reason is that when it's inlined it and you say, how did it schedule that code on the GPU, the loop mark is useless for that. It doesn't give you that information very easily. And it's just it's a fairly compiler-specific thing. So the idea of the routine directive is that you can provide a way of giving a routine that's somewhere else and saying it's already on the GPU and controlling the scheduling that, this routine should only be scheduled at the vector level because it will be called from another loop that's scheduled at the gang level. And routine gives you a way of sort of controlling this scheduling. So this library, it could be another routine in your code, it could be in a third-party library. But it would be a library that you're calling from within a parallel region. So there's some examples there. Another thing which isn't really specific to a the Cray architecture is, what if you want to write your code and you want to run it on multiple accelerators, and the tuning options are different for different accelerators? What do I do? In OpenACC 1, you just have to do hash if def, I'm running on NVIDIA, ACC parallel and some clauses, else I'm running on AMD, do something else. With OpenACC 2, there is this idea of device type where you can say the clauses after here apply to NVIDIA targets, the clauses after here apply to Radeon targets or whatever. You don't really use that on a Cray system because we've only got NVIDIA GPUs, but if you're going across multiple architectures, there's now that facility. Nested parallelism, well, you couldn't have a parallel region inside a parallel region in OpenACC 1. In OpenACC 2, they let you do it. The only real restriction to this is that you cannot, you have to be careful about the scheduling of it. Sometimes it can be a good thing, but quite often it can have a big impact on memory usage, so I would only use that carefully. I mean, this nested parallelism, there's examples of this, came in with CUDA 5, so there's CUDA 5 examples of doing the Mandelbrot set and whatever with nested parallelism, but use it with care. It can be done. The Runtime API, why have I put this here? Is this not important? And the answer is, I don't find it very important. You can do a lot with it, but you can do, for most codes, I can do it with directives. It's a set of library calls. The names all start as ACC underscore something. You can control accelerator properties. Well, there's only one accelerator to use on a Cray system, so I never need to change the accelerator. It gives you some finer-grained control of asynchronicity. That's one thing. You can use it for data allocation and movement. Usually you can use a data region or the enter-exit data, but there are cases where you really want to do something a bit weird, or you really don't want to have any memory allocated on the CPU, and then it can be useful. So there are various calls you can make to ask, what sort of devices could I use? What is the next device that I'm going to use? I'd like to use this type of device next. How many of these devices are there? All these sorts of things. You might use these, but you wouldn't on a Cray system. You could put them in, but there's only one sort of accelerator, so I never use them. There's ACC init, ACC shutdown. The Cray runtime does that for you automatically. You might choose to use the ACC init right at the start of your program if you wanted to get the GPU initialized early so that it didn't show up when you run your first kernel. Otherwise, when you run your first kernel, it seems slow because it includes the initialization time. So if you want to do the initialization early, you can call this. You don't need to shut it down on a Cray system. There's lots of ways where you can control how memory is used. Many of these are the same as the corresponding directive. So ACC update device is the same as pragma ACC update device. So they just duplicate it. I think the answer is some people like to use runtime API calls. The real reason they're there is because the compiler's using them, but they're exposed to the user. You generally don't need to do this control of memory. If you think you need to know where something is in GPU memory to pass this to CUDA, you actually don't need to do it because there's other ways of doing it that we'll talk about with directives. If you want to start messing about with the present table to say data is present on the GPU, there are ways to do this. But all of this is very advanced. All of the async wait, all of this sort of wait all, wait for particular handles, you can do these with API calls instead of doing them with directives if you want. The only thing that you can do with the API that you can't easily do with directives is to test whether a stream of tasks has finished. There's no directive to test for it. So you can use the runtime API to do a test to see, has it finished? And if no, I'll go and do something else. You can mock it up. You can have a spinning loop with And you can do that, but there is about the only case where that's something you can do with the API that you couldn't do with a directive. The host data directive is very useful because it is a way of saying, in this next bit of code, when I talk past you an array, I'm not passing you an array in CPU memory, I am passing you a pointer to GPU memory. The reason this is useful is because, for instance, you want to call a CUDA kernel to process some data that you put onto the, you used an OpenACC data region to put the data on the GPU, but now you want to say to the CUDA kernel, this is where the data is, process it please. And this is where the host data comes in. So what you do, here's my double the array example again. Here I'm going to double the values by calling a CUDA kernel. So what do? I say, here's a call, but when I make this call, please pass an address in GPU memory rather than an address in CPU memory. I have a CUDA-C wrapper here. It picks up this pointer, it passes it straight into the CUDA launch, the kernel launch. And here's my kernel. So here, I needed to know the exact address in GPU memory, as I would have got by using CUDA malloc. And this is how I expose it. I can use this use device. The important thing here is if I do call CUDA, I need to make sure the OpenACC has finished, run the kernel, and make sure it's finished. So I must put in the explicit synchronization steps. But that is how you can call CUDA from within an OpenACC program, because you've got an optimized CUDA kernel, or because you're not calling your own CUDA, you're calling the QFFT library or the QBLAS library or something like that. You do it in the same way. You put the call inside a host data region. The other time you might use it, and we'll see that, I think tomorrow I'll talk about using MPI with GPU buffers, the so-called GPU direct. And again, host data is a way to expose, here is the data on the GPU, the real location of it, to some other code or the library. So these words, I mean, OpenACC is powerful, robust, scary, hard. These aren't my words. These are the words of the compiler developer, who's also our representative on the language committee. There's a lot you can do. I mean, this last talk, OpenACC 2 brings in some stuff which is very powerful, but you kind of look at it and you think, God, this is impossible. I thought OpenACC was supposed to be easy. But the kind of lesson, I suppose, is that in doing these practicals, we got good performance speed-ups for codes without using this stuff. It's there. There's certainly use cases for it, either for more complicated codes or for particular performance tuning. But you don't need it for a lot of codes. So don't be fazed by it. Don't look at this book and flick through it and say, my God, where do I start? Should I be using ACC routine or not? The answer to start with is no. But as you progress, you may find cases where it is. And so, that's why I'm mentioning it here. I'm not going into it in the practicals because it is an advanced topic. And we've only had a day, and even in that day, we've not done everything. So, are there any questions on what I've talked about there? It's hard to ask questions when I've been so vague, I know. Go on. What you need is that, yes, in principle, but the stream handle is an integer in Fortran or C, and it is a particular type in CUDA, whatever, I can't remember what it is. So you need a way of translating between the two. That way of translating does exist, and there is a Cray specific Runtime API call to do that translation, to allow you to kind of insert a CUDA kernel into an OpenACC stream. But this was, for various reasons, this was not accepted into the standard for OpenACC 2. So this sits there as a Cray extension. I mean, there were a lot of Cray extensions that were accepted into OpenACC 2, but this one was not. I don't remember the reason, but it's not necessarily that it's horrible, nobody will ever accept it. It's just, you know, in every standardization process, there is a cutoff. At this point, we have agreed this. We want to announce at ISC, we must have a finished standard. So there is a way to do it within the Cray compiler, but it's not portable. Again, it requires, if people come back and say, this is very important, this kind of is how things get fed into the next standard. But when people say, this is not important, we're running short of time to discuss this standard, then these things get dropped. So if this is something that you think would be very useful because you need to mix CUDA and OpenACC and use the asynchronicity, then please do get in touch. Everyone looks stunned. There's been a lot of material today. I'm sorry, there is a lot of material. And as I say, it's hopefully it's been graded through the day enough that, you know, when you're old, like me, your brain is full, and after a certain point of the day, you can absorb nothing new. So hopefully, you know, a lot of you are younger, much more agile minds, but you know, you reach a point where you cease to get it. So I've tried to structure it from the point of view of an application developer. You know, what would you start with? What would you add later? And you know, if you only do the starting bits, how far can you get? And it's a fair way. It's a fair way. But then you get onto loop scheduling, and it all gets a bit more complicated. But it's like any optimizations. The optimizations are always more complicated. So tomorrow I'm around until about 11 o'clock, then I have to leave. Some of that time will be for discussions. I might spend a little bit of time talking about porting a parallel code, which does not involve much in the way of actual coding, but is more about the sorts of techniques, and it gives you some real use examples of using asynchronicity and the sorts of things you can do with that for an MPI code. What you find with an MPI code is there's a lot more scope for using asynchronicity, even where the serial version had none. So I may do that briefly tomorrow and give you a little bit of view of what OpenACC 3 might lead to and how it compares to OpenMP 4. But there will also be some time, so if you want to continue the practical work, you can do that. If you want to talk about your own code or other issues, I'll be around for those discussions. Or you can bend my ear this evening. So I think I'd better stop. I've outstayed my welcome, I realize, but I'd better stop there. Are there any further questions? A few. Yeah, I mean, please try it, and please, you know, whatever, you know, whether it's Hello World or something bigger, please feed back your experiences. Things that were good and things that were bad, but especially things that were bad, because we can improve it, you know. But